them together. When you write a Boolean expression like that, you're always going to get a combinational logic circuit. And it translates one for one with whatever you put into the Boolean expression into a logic gate. For example, the value sum here is A exclusive OR B. So here's A and B coming in, they're exclusive ORed, and that gets exclusive ORed with carry in. So you have exclusive OR driving another exclusive OR, and there's the sum output. So you can do a one-to-one correspondence between one of these logical operators and logic gates.
So
Yeah.
if we instead used a non-blocking for this combinational logic, might it accidentally synthesize a less efficient synthesis, or
No.
no?
The use of non-blocking for sequential logic has a completely different reason, which I'm going to get to shortly. If I have a design like this, which these continuous assignment statements we've already seen always translate into combinational logic, I could have used either one, and I would have wound up with this type of circuit. The reason why you want to use non-blocking for sequential logic is going to be obvious shortly. We'll get there. Shift operators. Now this is where you start to get into some surprises on what gets synthesized. And it depends on how you coded your design. So this is the left shift or the right shift. And what gets synthesized depends on whether the shift is constant or variable. And what I mean by that is I can say I want a constant shift, so I say shift left by 2-bit positions. If I use a variable, I can say shift left by y, where y is a variable that's going to be defined somehow. First example, and this will be a constant shift. I have an input data mux, which is 4 bits, and an output address, which is 6 bits. And in the continuous assignment statement, I state that address is equal to the complement of data mux shifted left by 2-bit positions. And I'll put this in here. I have hard-coded in a constant. Now you recall that when you do a shift, you're going to move everything over, in this case by 2-bit positions, and every shift you insert into the least significant bit a logic 0. How many would have expected this? The 2 least significant bits, just round them. The other bits have to go through an inverter because this code does say that you take the complement of it So if you look at the numbering here, I really do need to bring my glasses in. Address 3 here is the most significant bit, and that's the most significant bit of the input data. So there's address 2, address 3, address 2, then address 1, then 0, then 5 and 4. I will point out the way this was declared, 0 is the most significant bit. Right? Okay, so very simple, straightforward circuit if I have a constant shift. Now here's an example where I've got two inputs, memory data reg, which is 3 bits, amount is the amount I want to do the shift, and then instruction reg is the output. Now you'll notice here the shift amount is a variable. There's your circuitry. Considerably more complex. Notice that there are 1, 2, 3 macros that were used in that design. So if you are going to encode a module that does a shift operation, and the shift amount is variable, it's not hard-coded in as a constant, you can expect a much more complex circuit is going to get synthesized. Yeah.
What's the reason behind this? So amount is defined somewhere as 2 or whatever, and then why does it generate this complex circuit instead of generating this?
Because you'll notice that amount here is a 2-bit variable. That means the circuit that's synthesized has to be able to accommodate a shift of 1-bit position, 2-bit positions, or 3-bit positions. The same circuit, depending on whatever you put into for an amount. That's why you have to have a more complex circuit, because it's got to be able to accommodate all possible shifts that you can represent in however many bits you've given for the amount. Like anything else, when you add flexibility, you add complexity. Nothing's for free. Okay, now I'm going to define 2 terms here. And the reason I'm going to define those, these are terms that were used in the text to differentiate how you're specifying vectors. Let's suppose I have the following assignment. Okay, so I've got some vector M. I'm going to take bits 0, 2, and 9 out of that, concatenate them together, and that's going to form the 3 bits out of Y. Now, just to complete this, let me do the following declaration. So I have defined M to be 12 bits and Y to be 8 bits. Now, if you look at this assignment statement, I'm not assigning an entire value to Y, I'm only changing the 3 least significant bits. So this is referred to as a part select. And those are going to be referred to as bit selects, because I'm only selecting 1 bit. So a part select, you're selecting multiple consecutive bits. Okay? All right, now. I'll make a note. Non-constant part select is usually not supported. I've got constants in there. I don't have any variables. So let's look at this example first. Here I'm doing a bitwise exclusive OR of 2 4-bit inputs, and that's going to give me a 4-bit output. This is a bitwise exclusive OR. So as you would expect, you're going to get 4 exclusive OR gates. Each exclusive OR gate is going to exclusive OR a pair of the corresponding bits in the 2 inputs. Here I've got a part select. There's a part select. There's a bit select. And again, I'm going to get a combinational logic circuit. Now, I made the comment before that I'm not making any claims that the circuits that are shown are necessarily optimal. This is a double pair of inverters, and you could say, well, why didn't you just put wires in there? At any rate, there's a circuit that gets generated. Things change, however, if you have variable bit selects. So again, to recap, if my bit selects are constants, then I'm just going to wind up with a simple combinational logic circuit. If those bit selects are variable, however, it depends. if the variable is on the right-hand side or left-hand side of the assignment. Because depending on whether it's on the right-hand side or the left-hand side will affect dramatically what you get synthesized. Let me show you an example of what I mean here. In this example, you'll notice that the variable is on the right-hand side of the expression. And that's the circuit that gets synthesized. And you'll notice that it has 3 macros. And notice the note down there. A non-constant bit select on the right-hand side generates a multiplexer type circuit. Now here's a set of code where you'll notice that the variable is on the left-hand side. Completely different circuitry. And in fact, as my note says here, you get a decoder. So if the variable bit is on the right-hand side, you get a multiplexing circuit. If it's on the left-hand side, you get a decoding circuit.
Question, how is that different than when you mentioned you cannot have a variable on your left-hand side?
That's not a part select, that's a bit select.
Okay.
Remember, the part select, you're specifying a range of bits. Here, I'm just specifying 1 bit position,
Okay.
whatever address happens to be.
Okay.
So I can specify, there's 3 bits, so there's 8 possible values there. See how mem is declared? It's an 8-bit variable. You tell me the value of address, which is going to have a number of 0 through 7, and that's the only bit that's being assigned.
I see. Okay.
So this is not a variable part select, it's a variable bit select. Yeah,
And I just wanted to make sure, if you were talking about tick defines, those are going to be constants, correct?
I'm sorry, say that again.
If we use tick define num bits equals 7, and then we use num bits, that's going to be a constant?
Yeah,
Okay, I just want to make sure.
but I'm not sure why you would use that particular notation. For readability standpoints,
Yeah.
using just the decimal number, not that special tick mark, D, hex, B.
Oh, no, I meant if you, I thought that was what they were called, the tick defines, where you are, so that you can then later on change it to I'm making an 8-bit adder, but I want to make it so that later on I can change it to a 16-bit
Well,
adder.
the normal way you code that is just use the decimal number, don't use that tick mark, whatever.
Okay,
The tick mark syntax is used only if for some reason you want to specify the number as a set of individual characters rather than just telling me what the number is.
okay,
For tick mark B 0100 instead of just saying 4.
yeah,
If I'm going to do a shift operation or something like that, it's a lot more readable if I just tell you what the number is rather than use that special notation. In this example, we're now going to deal with conditional, where stop XM, if the reset input is a logic 0, notice it's complemented, then stop XM is going to be start XM exclusive OR with shift val. And if that is not true, reset is a 1, so the complement of it is 0. Then stop XM is start XM ORed with shift val. That's the circuit that gets implemented. You'll notice you have and, or. That implies a mux. So an if then else type of expression synthesizes as a multiplexer. Okay? Now, it turns out that a good practice is to include all variables in the always statement event list. Now you could explicitly enumerate them in that event list, or you could use the asterisk as a wildcard to make sure that you've got them all. I want to show you an example here. Let's suppose I did the following. And in this particular case, A is missing from that event list. Now, what I'm actually looking for here is that type of circuit. And I inadvertently left the A out of here. What you're going to wind up getting synthesized may be different than what you actually expect. And I've got an example here that I want to show you. I have two module templates here. It's my and one has A and B as inputs and Y as the output. And if I state always at A, if A and B, Y equals 1, else Y equals 0. That's just the AND gate implementation. But you'll notice that I only put one of the inputs in the always event list. My second AND gate is identical, except now I put A or B. If they change, then you do the AND function. So then I created a test bench where I instantiated both AND gates, and then I go through here and conduct an exhaustive test where I apply all possible inputs, 0, 0, 0, 1, 1, 0, 1, 1. And this shows the outputs. Now, so that we're clear here on the way these are instantiated, Y1 is going to be the output from my AND1, where I did not have a complete event list, and AND2, I did have the complete event list. So here's my inputs: 0, 0, 0, 1, 1, 0, 1, 1. Y2 is the correct encoding, where I have A and B both part of the event list, and you can see that only when the input is 1, 1 do I get a logic 1. But you'll notice here I had a logic 0 for all 4 inputs. The reason why is I left B out of this event list, so the input 1, 0 for A and B should produce a 0 output. But in my third test case, the B changed to a logic 1, but that isn't sufficient to trigger the always statement. So you wind up getting a 0. So in both cases, I'm going to get a AND gate implemented, a combination logic circuit, I guess I should say implemented, but I'm not getting the behavior I wanted because I left out one signal in the event list. So the way that you prevent that is to make sure that you have a complete event list. Okay. Let's take a 10-minute break. Juice. We're going to meet about 5 after 4. I'll show up.